Welcome to the third lecture of device materials part of the course Advanced Materials Chemistry. And today we will see solar photovoltaics. In the last class, we learned metal semiconductors and insulators. Then we saw what are direct and indirect semiconductors. Then intrinsic and extrinsic semiconductors. Intrinsic semiconductors are the semiconductors when they are in the pure form, and extrinsic semiconductors when they are the impurities are added to the pure semiconductors. Then donors and acceptors we saw. Donors are the materials which donates electrons to semiconductors. Similarly, acceptors are those materials which accept electrons from the semiconductor. So there is an absence of electrons, and in acceptors, holes are there. Then we saw non-degenerate and degenerate semiconductors. The carrier transport also we understood. Then we saw P-N type semiconductors, and so the P-N junction also, how the junction is formed. Then we saw generation, recombination, and lifetime of different carriers. Then metal semiconductor contact. We understood when a metal and semiconductor contacts are made, how the different parameters like work function, electron affinities, all these comes into picture. Then we also understood some important semiconductor devices, building blocks, which are semiconductor metal contact, then semiconductor, then heterojunctions, PN junction, and MOS structures, which are the main building blocks of the semiconductor devices. You will find in almost all the devices one or more of these building blocks. So with this, now let us start on the solar cells. So first, what is sun? Sun is, you can imagine a very hot body which is at a temperature of 5800 Kelvin. So we know from the basic physics that every body which is having a temperature higher than 0 Kelvin, it emits a radiation. That is the black body radiation. So sun is also, since it is at 5800 Kelvin, it is also emitting a black body radiation. And what is the source of this temperature? The source of this temperature is the fusion reactions which are taking place inside the core of the sun. So because of these reactions, a lot of energy is being generated, and because of that energy, the temperature is raised. And since this body is at 5800 Kelvin temperature, it is bound to emit black body radiation. So considering the mass, size, and all other things of the sun, the energy emitted by sun is approximately 4 into 10 to the power 20 joules per second. Now Earth is very far from the sun, so and it is exposed at one time. Half of the part of the sun is Earth is only exposed to the sun. So if we calculate, we see 1,73,000 terawatt of sunlight hits the Earth every day. So you can imagine how much energy we are receiving from the sun. So, and this amount is 10,000 times more than the total energy required by the world. So, if we can somehow tap this energy, and even a fraction of that energy can be make usable, we will have sufficient amount of energy for the entire world. Now, this the light, or you can say the radiation, which is coming to the earth, has a spectrum. Spectrum means spectrum is when you can say plot that radiation, the intensity versus the wavelength. So if we analyze that wavelength, if we analyze the incident radiation and we plot with using monochromator, we plot the spectrum, we get this kind of spectrum. So as it is at 5800 Kelvin, body heat is the radiation is emitted, black body radiation. So that is exactly you can say a curve. This curve is a black body spectrum of a body which is at nearly 6000 Kelvin. Now, so ideally we should be receiving this kind of spectrum at the earth. But what we receive is this spectrum, which is in the red form. Some parts are here, some parts are available, some parts something is missing on this wavelength. So why it happens? If we measure the spectrum just above the you can say atmosphere of Earth, in that case we get spectrum like this, the yellow one, which is very close to the black body curve, which is a black body curve of 5800 Kelvin. As soon as this radiation enters inside the atmosphere, there are several gases, and the gases absorb the radiation as per their molecular structure. If the energy of the certain radiation falls, which is matching with the energy levels, vibrational levels of you can say different gases, these will be absorbed. So these there that much energy is absorbed, some energy is scattered, some energy is absorbed. So these bands which we are seeing here, like this band, this band belongs to absorption at oxygen, this belongs to absorption of hydrogen, and these are also the absorption due to hydrogen and carbon dioxide and oxygen. And this part and the lower part, it is the ozone, which absorb in the UV part. And the fraction of this energy is typically 7% is in UV range and about 44% in the visible range, and remaining is in the IR region. So at the outer surface of the atmosphere, the energy received is 1353 watt per meter square. However, when you come down at the earth, it is actually much lower. So the spectrum at the outer surface of the atmosphere is called as AM0. And so the spectrum, solar spectrum, in this photovoltaic measurements, this spectrum is defined like AM and then certain number. So this AM is actually air mass, and 0 is this number. The next number is the value, how much atmosphere it has crossed the radiation before it has reached that point where you are actually defining. So this air mass is defined like this. Suppose this is Earth and this is Sun here. So when at noon the sun is the radiation which is coming from sun is this much amount of atmosphere it is passing through. When in the evening or at some other point of time, suppose it is passing, which is slightly bigger than the distance at the time of when the minimum distance. So the minimum distance is suppose x. In that case, the ratio of y divided by x or y by x, this refers to the air mass, and it is written after AM. So if I am writing AM0, it actually means that it has not crossed any atmosphere. So the value of this will be AM1 because it has crossed exactly 1 atmosphere. Yeah. So we can define it AM y by x. It refers to mass of air with respect to vertical height of atmosphere that light has to transverse before reaching the ground. So AM0 is sun incident energy at the outside of the atmosphere. The value of this is, as I shown earlier slide also, it is nearly 135 milliwatt per centimeter square or 1350 watt per meter square. AM1 is when sun is here at the zenith, and in that case, it will actually completely 1 atmosphere distance will be traveled by the radiation before it reaches. So this will be called as AM1, and normally in the standard is AM 1.5. So that is what is that? That means the distance traveled by radiation is 1.5 times the distance of minimum distance. So the intensity at that time of radiation received at the ground is about 88 milliwatt per centimeter square. But it also received, this is the direct radiation which is received directly from the sun. But we also receive some diffuse light, and therefore at this 1.5 global AM 1.5 global standard, the intensity received at Earth is nearly 100 milliwatt per centimeter square, which is a standard, and mostly in photovoltaic measurement, this intensity is used. Now this was the solar about the solar energy, received at that. Now what are solar cells? Solar cells are devices that takes light energy as input and convert it into the electrical energy. So suppose you have a sun, and then light energy is received at a certain device, and the device it converts into the electrical energy. That device is called as solar cell. The solar energy received on the earth is about as I said earlier, about 1000 watt per meter square or 100 milliwatt per centimeter square, which is AM 1.5G standard. Since we are receiving that much energy, about 1 kilowatt in per meter, so that is a very you can say big amount of energy. If you consider a small bulb or nowadays LED bulbs, which are hardly about 15 to 20 watts. So the energy which we are receiving in 1 meter can actually give sufficient, this energy is sufficient to actually glow 50 such bulbs, 50 bulbs of 20 watts LED bulb. Usually we use about one to two bulb in per house, but that is the case when you can convert the entire solar energy into the electrical energy. But that is not the case. Solar power cannot be used. It cannot be used in the night time. So what you have to do if you want continuous supply in the daytime, you have to store the energy and in the form of some storage, mostly in the form of batteries, and then you can use it in the night time. So you need uh, extra batteries. And solar panels are relatively expensive. Energy to be stored in batteries, as I already said, so you need to spend a little bit more, and then this DC has to convert it back into AC. So some efficiency loss is there. They need a large area of land to produce more efficient power supply. Issues with tilt alignment of the panel. Usually, it starts in the morning from east, and in the evening it sets in the west. So, uh, can you all the time? Ideally, if you can uh, keep on tilting or aligning the solar panel as towards the sun, it will be the ideal situation, but that is not possible. So therefore, there are certain issues with the tilt and alignment of panel. Can it be done automatic, or if you fix, there are a lot of issues. So there are several issues. Then there is a cleaning issues also. Uh, if there is a large power plants where several thousand solar panels are fixed, then uh, usually these are in the desert areas, and there is a lot of cleaning issues. Very difficult to clean because dust with the dust, uh, it falls on the panels, and the energy uh, conversion becomes less efficient. Now, what are different photovoltaic technologies? So the solar cell technologies are divided into three different generations. First generation, which was starting from somewhere in 1950s. Then secondary generation, which is based on the thin film. First generation were usually based on wafer based, where single crystals were used. Second generation is thin film technologies, and third generation, which is new emerging technologies. In first generation, monocrystalline silicon and gallium arsenide solar cells were used. Polycrystalline silicon solar cells were also used in first generation wafer based, where it is thicker, you can say, still polycrystalline wafer. In second generation thin film based solar cells, amorphous silicon solar cell, cadmium telluride solar cell, and CIGS solar cell. These are most commonly used solar cells in this generation. And third generation is it is at present where we have organic solar cells, dye-sensitized solar cells, perovskite solar cells, and quantum solar cells, quantum dot solar cells. The research is going on all of these solar cells with full swing, and the efficiencies are also relatively high, or you can say comparatively high. But there are certain issues regarding stability, and also the degradation issues. Stability is one issue. Degradation is another. Degradation of a component is another issue, and there are certain other issues because of which the commercialization is taking a little bit of time. So let us first understand how a typical solar cell works. Yesterday we saw how a PN junction is formed. So a silicon solar cell is based on the PN junction cell only. So suppose we have a p-type material and n-type material of, you can say, same compound, let us say silicon. So now we have p-type silicon here and n-type silicon here. So n-type silicon means there are electrons uh, as a majority charge carriers, and p-type silicon, there are holes which are majority charge carriers. So the Fermi levels will be in n-type silicon, it will be close to the conduction band, and p-type it will be close to the valence band. Now, when we fuse them together, what happens? See, the Fermi level are now at the you can say different. There is an abrupt change, so which cannot be a true picture. Ideally, when you fuse these things, the Fermi level must align. So now, if Fermi levels are aligned, so there is an abrupt change in the band. So that is also not possible because in this situation, electron will start to flow from one place to another place, as we explained yesterday. That is the diffusion and drift. Because of this diffusion, the voltage, a built-in potential will be developed, and there will be drift and diffusion. Both the processes will take place, and under thermal equilibrium, you have this kind of situation where a p-type semiconductor and n-type silicon, there is a small, you can say, area where the band will be like this, and this will be the Fermi level. Now this we can consider as a solar cell. So now we take contacts at two ends. Now can we take this contact? I just want to know because we discussed yesterday also that when we this contact is of metal. So when we fuse a metal with the semiconductor, there will be a Schottky barrier. Because of that, it will also behave like a rectifier. Similarly, here also it will behave a rectifier. So these will be actually two back-to-back rectifier. So there will not be any current. So in order to make this junction, a different technology of is used where this junction is, you can say these contacts are made ohmic contacts. So suppose we have made now ohmic contacts, and this is the solar cell. There's a load. Now what happens if radiation falls? Then you will have electron and hole pair generated. The electron will be excited to the conduction band, and then it will be swept away by this built-in potential, and then the electron will flow from in this circuit through this load, and similarly the hole will flow from the other side, and it will a current will be flowing through the external circuit. So this is the way how a solar cell works. Now, what are important parameters for a solar cell? Suppose you have a solar cell. Now, you need to characterize the solar cell. So you need to characterize the solar cell. So there are certain parameters which are important parameters for any solar cell. We will see for every solar cell you will be having those parameters. Now, suppose this is a solar cell, and sunlight is coming from this side. So you have put a circuit here. This is p type, n type, and there is a contact this side. So you have put a circuit here. Now you are illuminating. Now what happens? You remove this. The maximum voltage which can, by removing this resistance, you just make the circuit open circuit. So the maximum voltage which a solar cell can produce, that is called as the open circuit voltage. So that is one parameter. open circuit voltage. So for that, you need to remove this resistance, and then the max, in that case, it will be the maximum voltage which will be the next one is you just short this, and so in that case, if you short these two terminals, in that case what you will get is the maximum possible current which is generated by this solar cell. This current is called as the short circuit current. So open circuit voltage is that voltage when there is no current drawn through the external circuit, and that is the maximum voltage which has been produced by the solar cell. Next thing is the short circuit current, which is the maximum current which can be drawn from a solar cell, and the voltage obviously has to be zero because you have completely shorted it through a zero resistance, ideally you can say. Now we want the maximum voltage and we want the maximum current, but that is not possible. When we saw the open circuit voltage was at this point where we were drawing actually zero current, and short circuit current was at this point where we had zero voltage. So if you see, though we have got maximum current or maximum voltage, but power drawn from the solar cell is zero. But what we want certain power from the solar cell so that it can be utilized in some application, or some electrical appliance can be run through this. So now if we start drawing power, or you can say by varying this resistance, we try to draw the curve, that IV curve is followed, it follows this path. So this I am trying to present when by varying the this load value, I can actually draw this curve. So now we see there are different points P1, P2 and some P. So at this point, what is my power? Power is usually V into I. So V into I, so this will be the area. This area will be the power drawn at this point. Similarly, this area will be the power at this point. So by following this, we get a point where this area is maximum. So ideally, we want to operate my solar cell on this point where I can draw the maximum power. So this, for this particular point, the area, this area which has been, or this power which has been actually being drawn from the solar cell, and the ratio of ideally theoretically power which we want, we want theoretically the voltage should be VOC, the maximum voltage, and the current is ISC, the maximum current. So that should be this power. So the ratio of this area to this area is called as the fill factor. The fraction of the maximum power that can be extracted from the cell, and it is defined as the, so Im into Vm divided by ISC into VOC. So now we have three parameters: open circuit voltage, short circuit current, and fill factor. So efficiency can be now found out by what is the maximum power drawn divided by the power irradiated. So power irradiated we can get from the whatever irradiation we have got, suppose at 1.5 G AM 1.5. So in that case the power will be 100 milliwatt per centimeter square or 1000 watt per meter square. And whatever is the maximum power which can be drawn, that is from the solar cell, VOC, ISC multiplied, and then multiplied by fill factor, and then divided by the irradiated power, you get the efficiency of a solar cell. This is a equivalent circuit for a solar cell. So solar cell is actually a current device, where this diode is added in this way, and then you have two you can say resistances. One is series resistance and another is the shunt resistance. So this is the equivalent circuit for the solar cell. Now, what are different processes in a photovoltaic energy conversion? This means when radiation falls on a solar cell, how actually it is being converted into the electrical energy. First is obviously the light has to be absorbed. So the or radiation has to be absorbed. So first step is the absorption of light in a material, and because of this absorption, electrons or can say excitons, in some case excitons are created, but let us for the time being presume only the uh, silicon part. So electrons and holes are generated. So some transition. Then first thing is that now electron and hole pairs are generated. So this is the excited state energy should be converted back into free positive and negative charge carriers. They are still bound. Though electron hole pair has been generated, but still it is bound. So it has to be separated. Then there should be a mechanism by which positive and negative charge carriers can be you can say moved from one place to another place, and it can be brought to the electrodes, and afterwards the fourth is the collection of charge carriers on the electrodes. So first is absorption, then after absorption creation of free electron hole pair, then movement of those electron hole pairs, and then the finally collection of those electron hole pairs. And once this has been collected at the electrodes, and if there is a load applied in the circuit, these are bound to move through that load. What are different losses? As I said, the first thing is that absorption. So if radiation is falling on a solar cell, what it can do? It can get absorbed also, or it can get reflected away also. So if it has been reflected, this is lost. So, or there's another way. The light, though it has been gone inside the solar cell, but the thickness is less, or there are some other regions that could be the band gap also, and because of that radiation has been you can say leaked out. So there are two losses when the radiation is reflected from the surface, or it has not been absorbed, but actually it has, we can say, passed in. So this is the a formula which we know from our earlier physics classes, that if the N1 and N2 are refractive indexes. N1, suppose it is air, for it will be 0. Then the total reflection amount will be given by reflected amount of radiation will be given by simple this formula. Now, what are solutions for this? First solution is an anti-reflection coating. So anti-reflection coating is a coating made over the surface where this reflection is stopped or minimized by making some lambda 4 or different. There are different techniques by which ARCs are created. One is that you stop reflection by that. Next is the texturing the top surface. So if you have a surface, if it is a flat surface, and then if you make a jig this kind of surface, so if light falls in that way, it will go back here, it will go back here, and there is a more probability that it will be absorbed. It will be absorbed inside this surface. And by doing this, actually, you are uh, creating more area. So texture is also another thing, texturing the surface, and then you can use concentrators also. Concentrators are those you can say assemblies, like if you can say uh, the convex lens. If you just concentrator, I am trying to explain in a simple way. Suppose you have a convex lens, and then with the help of the convex lens, a large amount of radiation can be concentrated into small spots, small areas. So concentrators are such assemblies which actually guide a large solar radiation into the small area. So in that case, you can use a smaller solar cell for converting a large input radiation. Now we come to the how the absorption of light takes place inside the material. What plays important role is the band gap of the material. So if a radiation which is falling on this, suppose you have a material which has this structure. It is a valence band, it is a conduction band, then Fermi level, and it is having this much of band gap. So if radiation is falling on this material and the energy of the radiation is actually less than this energy, in that case, what will happen? This radiation will not be absorbed. Because this electron, as we saw yesterday and day before yesterday also, this electron, in order to accept this radiation, this electron need to have the energy level, a valid energy level, which is this present energy plus this energy. So if you add this energy, there should be a valid energy level, but it is not there. So at least this much energy is required. When you get a photon of this energy, it will be absorbed and electron will actually, you can say, promote to this level. So band gap plays a very important role in absorption. So first thing is that if you want to absorb the maximum amount of radiation, then in that case, what should be the band gap? If I ask, the band gap should be 0. If the band gap is 0, in that case, whatever absorption, whatever radiation has been incident on a material, it will be totally absorbed. Like copper, suppose you have a copper plate, and on that copper plate, radiation is falling, the entire radiation will be absorbed, nothing will be found. So one is the band gap. So band gap plays an important role. But if you have a zero band gap material, can you have a solar cell? No, because how then you will actually separate those electron hole pairs? You need some built-in potential also. And the next thing is the thickness of the material. So thickness of the material also plays important role. If the thickness is very low, though very low, and though band gap is less, but then also some radiation may be leaked out. So it follows the formula is like this. If it is I0 is suppose intensity here, then intensity at this point is given by I0 e raised to the power minus mu t, where t is this thickness and mu is the linear absorption coefficient. So if we see band gap of different materials which are used in the solar cell. One thing is that, as I said, copper cannot be used because though it is having zero band gap, it will absorb entire solar spectrum. So one condition will be totally fulfilled, but there will not be any mechanism by which this electron which you have promoted can be effectively utilized in some external circuit. So we need to have certain amount of band gap. We have to trade between how low band gap we can use in the solar cell, and uh, uh, there are some other parameters also which slowly you will come to know. So so for like silicon, the wavelength is the corresponding wavelength. The band gap is, as we saw, 1.12 electron volt, and the corresponding band gap is band gap, you can say wavelength, h c by lambda, if we say, the corresponding wavelength comes about 1100 nanometer. So that means if you have a silicon material, crystalline silicon material, all the radiation uh, which is having you can say 1100 nanometer wavelength, or less, it will be absorbed, because lesser the wavelength will be the more the energy. So that, but any radiation, the wavelength more than 1000 or 1100 nanometer, it will be passed through it. So that entire spectrum, like suppose this was the my solar spectrum which I showed in the first slide, Anna. And if I use silicon solar cell, in that case, what will happen? Only this part, only this part of the spectrum will be absorbed, and entire this part of the spectrum will be lost. So straight away, if I say, hey, I am somewhere here, so it is maybe 20 plus 44, 44% plus 20, 60 and 7. So it is nearly 70% of the spectrum is only absorbed, or maybe and the remaining 30% or 25% has passed through the solar cells. So the maximum efficiency possible will be 75%, not more than that. That is the, when we consider all other afterwards process, ideal processes. So there are different materials with different band gaps. Silicon is this. If you want to use indium phosphide, it is this wavelength. Gallium arsenide, it is 1.42 is the electron volt, which is corresponding to this energy. So this entire energy, or if you use gallium arsenide, this much energy will be only you can say absorbed. All other will be passed through it. Now, what are different loss mechanism in a solar cell? Almost everything is explained in a crude way, but I want to put in this slide. So suppose light is fallen on a solar cell, it can reflect away. If it reflect away, this is total loss. So this is optical loss. Then if it is not reflected, then it can actually go in the material, but it can pass through it. So though it has been absorbed, or it has not reflected, but the photon has not been absorbed, that is also a loss. So this, both these comes under optical losses. Now suppose photon has been absorbed, so it will create free charges. So now once the free charges are created, they can recombine also. Who's stopping? Suppose electron hole pair is generated, that that hole can recombine with the electron. As we said, these have certain lifetime. Yesterday we saw the setup for lifetime measurement also. That's why whatever we have studied yesterday, though it was looking distributed topics, but all has certain importance in case of semiconductor devices. So now these charges, the electron and hole pair which has been generated, this has to be collected before they recombine. So if they recombine, this is lost. If you have separated them due to the built-in electric field, then these charges, this can again recombine while movement also. So first thing is that they can recombine at the electron hole pair immediately after that, and then they can recombine in the while they are moving also. They can recombine with certain traps also. There are some other recombination centers available in the crystals, different kind of recombination centers. So they should not recombine there also. Then if they do not recombine, then they will reach at the electrodes, and then so this will be then so these losses here, these are electrical losses. I can say the optical losses. There are two kind of losses: electrical losses and optical losses. The recombination, as I said, is possible. It can be radiative recombination where an photon is emitted. It could be trap assisted where the trap is there. Normally, these are non-radiative. The surface recombination or OZ recombination. Then there is another issue that if the temperature is increased of the surface, then also the efficiency changes. So all these loss mechanisms need to be minimized in order to have a good you can say high efficiency solar cell. So as I explained in previous slide also, so suppose this is my radiation which is falling. If the radiation, the energy is less, then we understood very well that this will not be absorbed and it will pass through. But what if energy is more than exact band gap? If it is exact band gap equal to Eg, in that case it will be absorbed fine. Electron hole pair will be generated. But if the energy is more than Eg, more than the band gap, in that case what will happen? The electron will be you can say promoted from this space to the corresponding energy which is higher to that. So this will be the photon energy. So like here, an electron has been, you can say, promoted from this place to this place. So now this energy immediately. So what has happened? A hole is created from this point, this place, and electron has been placed on a higher, you can say, electronic level, electronic state which was there. Now immediately this electron which is at the higher state, it will come down to the bottom of the conduction. Similarly, this hole which was here, this will also immediately come down to the top of the valence band. And how, when this comes from this to this, and similarly when this electron comes from this place to this place, this energy difference goes in form of heat. Similarly here also this much energy is lost in the form of, generally in the form of heat. So then this much energy is again lost. So in ideal case you should be having exactly photon energy equal to the band gap. If energy is more, it doesn't make difference if you are having 1.1 electron volt photon or 1.5 volt electron volt photon. They will create only one electron hole pair, and that energy of 0.4 electron volt which was an excess, it will go in form of heat. So this is also a loss. So First is spectrum loss, which has not been absorbed. It is anyway waste, which is if the energy or you can say radiation energy is less than the band gap, then it will anyway pass through this. So and next is if it is having higher, it is emitted in the form of heat, that is also lost. And then there is a impedance matching. See the current also, in order to flow the current, the impedance matching should be appropriate. Otherwise, there will not be the maximum power transfer. So for that, you need to have shunt resistance and series resistance, the optimum values. And recombination loss is like the if this electron and hole pair, they can recombine also. So the recombination loss should be minimum. So these are, but everything is there. You cannot have that. There will not be any recombination. Similarly, you cannot have the photon with energy higher than the band gap energy. So for every material, in that case, Shockley and Quachier, they calculated the theoretical limits for each materials. And then there is another thing, when the temperature of the cell rises, in that case, it also start emitting the black body. So that also plays an important role. So now if you see for different band gap materials, so if the band gap is between here it's between 1 and 3 volts, so this much is the only usable power which we can have. And this much will go in the this much will go in the like form of those photons for which the energy is less than the band gap energy, and this much amount of energy it goes in the relaxation means in the thermal loss, and the other losses are for this one. So if it is 100%, this will be the maximum possible. So this Shockley and Quachier, they calculated for different materials. The limit is, so for by considering or all the losses, in case of silicon, suppose we can have maximum nearly this much efficiency. For gallium arsenide, we can have this much efficiency. And if we have a germanium, if we want to make a solar cell of germanium material utilizing N-type and P-type germanium, then the maximum possible efficiency using a germanium solar cell cannot cross 21%. That is also theoretical when every other thing is perfect. So this is the Shockley-Quachier limit for maximum efficiency which can be obtained using a solar cell of these materials. So now what are the desirable property for good solar cell materials by considering all the previous discussion? For an appropriate semiconductor material selection, the optimum energy band gap matching with the solar energy is very important. So the band gap should be matching with the radiation. Now your radiation is also in a very look as a long range with containing a wavelength starting from UV to IR to microwave region. But you have to see that where your radiation falls maximum. So first is optimum energy band gap, which is matching with the solar energy. Then their high absorption coefficient materials are required. The mu value should be as high as possible so that you can absorb the radiation in a small thickness. Then carrier mobility should be good. Carrier mobility means, as we learned yesterday, mobility is the capability of moving the carrier, or you can say the way the carrier moves inside the material. So then large carrier lifetime. Large carrier lifetime means they should not recombine. If carriers are generated, they should stay longer so that they can be swept away by the built-in potential. Large built-in field for effective charge selection. If you have more built-in potential, in that case, the electron hole pair can be separated effectively. So this place, this built-in potential is, it depends on the Fermi level difference between N level and P level, N type and P type materials. Then there should be a large diffusion length, and then small surface recombination. There are some certain other considerations also. Reflection losses, as we told in, we saw in that slide also, anti-reflection coating, textured surface, multi-layer coating, these helps in the reflection or radiation loss from reflection or optical losses. Then in order to make better transport, the series resistance of the solar cell can be optimized by using better metallic grid design, and also using very high conductivity contacts with of course the ohmic contacts. Then transparent conducting coatings are also important for N-type, ITO, tin oxide, zinc oxide. These are usually for the organic solar cells. These things are more important, and so TCO's coatings are also important. Now, based on the types of crystals used, silicon solar cell can be classified into three categories. Number one, single crystalline silicon solar cells, polycrystalline silicon solar cells, and amorphous silicon solar cells. Single crystalline solar cells are those solar cells where a monocrystalline silicon crystal is a pure single crystal from which the entire entire solar cell is made. Since the monocrystalline is pure and defect free, the efficiency of this kind of solar cell is the maximum. How a solar cell is fabricated, starting from the wafer thing. Let us see here. So suppose I have a p-type silicon wafer. So wafer, we will see in maybe somewhere in fourth lecture how the crystal is converted into the wafer. Wafer is a very thin slice of a semiconducting material, which is used for the device formation. So now let us consider a silicon wafer. So normally the silicon wafers which is purchased from the market have damaged surface. So these damaged surface are from both sides, they are actually sawed. So after that you get a wafer in like this. So you have removed the damaged surfaces. Now after that you do texturing. Texturing can be done by different methods. Sandblasting or some other methods are there by which you can do texturing. So this texturing is done so that you have light falls on the more area and the less reflection. So to avoid the reflective losses, the textures surface is done. This is in like in this kind of thing, this wafers, it can be it is more convenient to do texturing by an etching process, because for silicon etching is relatively easier than using other texturing methods. So etching can be easily done by acids. Then after this surface is textured, then by phosphorus diffusion, it is placed inside a rich source of phosphorus. A thin layer of phosphorus is actually you can say phosphorus is diffused inside the layer, top layer. So now you have a surface, you have a p-type silicon, you have this p-type silicon, and over that a lot of phosphorus has been diffused, so now it has become n. So now it is p and you have now n surface over that. Now if you see this n, it will become conducting from this side, so we need to cut, we just cut it this part from, so this as is cut down. So after removing this, you just cut it. Then after that, an anti-reflection coating is done on this surface, that can be tantalum oxide. Then after that anti-reflection coating, a conducting paste which is silver, but there are some, it is step by step, there's two steps, and a paste is with a conductive paste, and then electrode is printed over this. Then you have a back electrode also with the silver and aluminum from this side also. So you have, though it is P, but it is fine. And then so you have, after that you do you give a heat treatment to this. So that way you can generate a this is a complete fabrication process of single crystalline silicon solar cell. So this is a typical view. You have SiO2 layer, then aluminum electrode, and then this is the texture of the top surface. And for a usually all of or most of these silicon solar cell follow this you can say IV curve, because the band gap is very precise, and the fabrication process is also very standard. So you get the curve like this in silicon solar cells. So about nearly 30 to 35 milliampere per centimeter square current, and then about you get about six about 600 millivolt of open circuit voltage. So the efficiency is here, if you say, is nearly 14.5% for this time. In our BRC also, a lot of work was done in fabrication of solar cells, and this work was started somewhere around 70s when the space applications or our space program was initiated. And that time nobody was giving solar cells to India. There was embargo also in between, so it has been thought that can we develop our own solar cells. So this activity was taken up, and space quality silicon solar cells of this site was developed using this was a general specification of the silicon. This is from the standard documents, and then we followed the fabrication steps where phosphorus was diffused and the 0.3 micrometer thickness n-type layer was made on the p-type surface. Then the front contacts were made by titanium, palladium, and silver, 3 layers, and the thickness was nearly this. And then anti-reflection coating on the front side was given by tantalum oxide, and it was done by thermal evaporation. Then the cells were cut into rectangle square size, and the efficiency of those cells was nearly 14.5%. And this is the process. This is the full process, and this was started in 1970, and the technology for entire thing was transferred to outside company in 80s. So within 10 years, we could develop everything. So this was the same thing which was I explained there. So material was P-type silicon, and the process gas furnace, POCl3, thermal evaporators, mask, titanium, palladium, silver, tantalum oxide. These were utilized. The substrate P-type original substrate, and then this substrate cleaning. Then it was given a heat treatment at 850 degrees centigrade, and the nitrogen was flown through this, and then the nitrogen was actually passed through the POCl3 so that it takes some certain amount of phosphorus on a optimized flow rate. Then P-N junction is formed because you have a P-type silicon substrate over there. This is being flown. The phosphorus is being flown at such a high temperature, and then backside contacts. These all were developed, and the standard solar cell were made, which the photograph is in the next slide. I can show. So these are the solar cells which were developed in 1970s, between 75 to 82, 83. And these photographs of photograph for these solar cells are from like last year, last to last year. So these solar cells were used, and these were used in different satellites, Bhaskar, Rohini, etc. And the technology was transferred in 1984 to Bangalore. So we have in BARC also we have developed. See, all these solar cells are working. So if I say after so many years, 37 years, the same solar cell, there are several solar cells, such solar cells are available with us. So if I try to test the reliability for those solar cells, because those solar cells has been used in the space applications. So reliability is very, very important. This should work for a longer period of time. Then it should have very high radiation hard. There is a lot of input intensity variations, because when a solar cell see in the space, if it see sun, it it is at you can say see very high intensity. At the other time, it can when it is the other side not seeing sun, it is at a very low temperature. So there is a you can say it has to qualify on the temperature variation, intensity variation, should qualify all those things. So those solar cells which were actually made about 35, 37 years ago, if you see today also, these are in our lab and we use them. So the efficiency, you can say the value which was in 84.6, now it is 0.57. This is very close. So efficiency, it was 13.7, now 12.1. So you can see that even after 37 years, the solar cells are working fine, perfectly. There is this variation could be due to some statistical error also. So that shows that silicon solar cells are actually very reliable. And their long-term stability is also good. So they can work for at least 40, 50 years. That is proven. It can go for longer time also, but 40, 50 years, 37 years, I have already shown you. Now this was for the single crystalline solar cell. Single crystalline is where you use single crystal wafers. Single crystal wafer is very expensive. You need more material also, and then there was the technology at the same time. It was developed the polycrystalline material. What is the difference between monocrystalline and polycrystalline? That you know very well. So monocrystalline is suppose throughout the entire material it is a single crystal. However, in polycrystalline, one can say there are several small crystallites. Grains are though during you can say within that grain they are single crystals, but over the entire you can say substance there are several or thousands or sometimes millions of the grains with different orientations. So polycrystalline is though on a very small level they are single crystalline, but overall it is not single crystal throughout the material. So compositional control is less stringent in these. Polycrystalline has certain advantages also, and then these are less energy intensity process. For single growing of the single crystal is very energy intensive process. We will see in one of the lectures that how the crystal is grown. So you need big instruments. Temperature need to be raised to very high. So in order to melt that. So these are making polycrystalline silicon is cheaper, relatively cheaper, uh, very cheaper in fact, as compared to making single crystals. Single crystal making is also very difficult. So in polycrystalline solar cells, liquid silicon used as a raw material, and polycrystalline silicon was obtained followed a solidification process. So how this process is done? You just take silicon and increase the temperature to melt it, and then just solidify it. Now, once you solidify it, then you will get the polycrystalline silicon. In order to make a single crystal, what you have to do, you need to have a seed. You need to, after melting, you need to keep the melt at that high temperature for a very long time. Then you need to have put a seed and then slowly pull the crystal out of it. So the material contains various this material which you have just poured or solidify from melt. It will contain various crystalline sizes, and hence the efficiency of this type of cell is less compared to the monocrystalline, but it is not that less also. But issues are polycrystalline material quality is poorer because of the crystalline defects and metallic impurities, and the diffusion length for both electrons and holes are lower as compared to the crystalline silicon, and texturing is more difficult because different exposed crystallographic planes. So the planes are different. Texturing is, as I said, the texturing usually in silicon is done by etching. But etching depends on which plane you are exposing to the solid, so to the acid. But now, when it is a polycrystalline mass, you do not know the exact plane because it is not a single plane. So therefore, the texturing is difficult, and you can do other methods of texturing, not actually acid etching or sandblasting kind of thing. Now, the fabrication process is like that. This you have see, you have taken a material, you have melted it, and after that you have simply poured it inside a container. So suppose this becomes polycrystalline. This is now, till now it is liquid, but within a short period of time this will also become solid. So now whatever this chunk you are getting is the totally polycrystalline mass. After that you remove this from that, so you will get a brick, and that brick, this much big, you cut it using saw or diamond saw or some other cutting tool, and then you make. So materials cast into rectangular blocks. This is a rectangular block and are cut in, polished in the making solar cells. Efficiency of solar, this kind of solar cells are typically 4 to 6% less than the single crystalline solar cells. And because there are a lot of grain boundaries are there. And if you see the difference, the photograph of polycrystalline silicon and monocrystalline solar, they look distinctly different from each other. Efficiency, Typical monocrystalline efficiency is 25 to 26%, polycrystalline is 22 to 20. So as I said, about 4 to 6% difference in the efficiency. Now the next come is the second generation, which is the thin film solar cell. Why thin film is required? Because number one, to reduce the material quantity, to reduce fabrication cost, and to renewable material properties. Important thin film solar cells are amorphous silicon solar cells, cadmium telluride solar cells, and copper indium gallium diselenide, CIGS solar cell. We will quickly go through each of these solar cells. So if we see the monocrystalline silicon lattice is like this. And then if we see amorphous means they are not following any long range order. And then they are silicon, and then they are unsaturated bonds. That is called as the dangling bond. So there are several bonds. These bond has to be actually saturated with the hydrogen. So these are hydrogenated amorphous silicon is used in the this kind of solar cells. So this is typical absorption spectrum. As I said, the absorption plays a very crucial role in the efficiency of a solar cell, because whatever is being absorbed, only those can be converted into electrical energy. So suppose for this copper indium selenide, the absorption is up to this level. Gallium arsenide can absorb only up to this energy, and then crystalline silicon can go up to this point, 1.1 electron volt. And so there are different absorption spectrum for different materials. So amorphous silicon was obtained by depositing silicon film on a substrate like glass plate. And how do you deposit? You can deposit by different methods. Could be sputtering, it could be other method, evaporation also you can deposit. So and then the advantage is that you deposit very thin film. The material loss is very low. So deposition can be sputtering, glow discharge, vacuum deposition process. It has higher optical gap of about 1.8 electron volt compared to the crystalline silicon, which was having 1.1 electron volt. And it has very high absorption coefficient, which is about 100 times in that. Let's see crystalline silicon. If you want to compare the thickness, this is about nearly 1 micron thick solar cell. You must have seen in the earlier can say calculators, there used to be a small solar cell which used to give the power to the solar cell. These are the amorphous silicon solar cells, thin film solar cells. So the thickness of the silicon film deposited is nearly about 1 micron only. If you want to see, if you want to just realize how 1 micron looks like, the human hair, our hair is typically 75 to 100 micron thick. So just imagine how thin layer of silicon is deposited, and then it is working as a solar cell. So the dangling bond which I showed can be reduced by hydrogen doping, and so it is called as the hydrogenated silicon. Then lower carrier lifetime and mobility in compared to crystalline silicon in these amorphous silicon solar cells. So as a result, the efficiency of amorphous solar cell is much lower than that of the other two cell types. These are used mainly in the low power equipment such as watches and pocket calculators. I already said. So there were three. One is the single crystalline solar cells, which is having highest efficiency. Then we had polycrystalline solar cells, that is having efficiency somewhere in between. And then we have thin film solar cells. This is amorphous solar cell, which is having the much lower efficiency, but the thickness is very, very small in case of that thing. Then this is the typical picture of a amorphous thin film solar cell, which is of silicon. So now you have p-type and n-type material. In between these two materials, a very thin film of amorphous silicon is sandwiched. So it becomes like that. There is a because of this p-type and n-type material, a built-in potential is developed, and when the light falls, an electron hole pair is generated, and this is under this VBI or built-in potential, these electron and hole pairs are separated. And these are then given to the external circuit. Here you have a metal contact, here you have this. So this is a typical you can say structure where there is a metal contact, then you deposit n kind of n type of layer, then intrinsic layer, pure silicon, this one, then p type layer, very thin, and then transparent conducting oxide. Transparent conducting oxide are those materials which are actually transparent but they conduct. So then you can have an you can say electrode from this point and electrode from this point, and then put an external circuit here. So just to see a comparison between monocrystalline, polycrystalline, and amorphous solar cells. So crystalline order, as far as the crystallinity order is concerned, monocrystalline is having single crystals, and polycrystalline has a tiny small crystals, and but amorphous is absolutely no crystalline order because they are amorphous. The thickness of the active solar cell is about 50 to 300 micron, and same is the thickness for polycrystalline solar cell, silicon solar cells also. However, for amorphous silicon, the thickness is less than 1 micron. The efficiency ranges from 25 to 26% for monocrystalline. And if you recall, with the Shockley-Quezier limit, how much is the maximum efficiency which we can achieve using a silicon solar cell is around 32 to 33. So it is very close. 26% is reasonable in that case. And then polycrystalline we get 22 to 23%, and for amorphous we get nearly 7 to 13%. But these are a very you can say small solar cells which are used at a localized place where very small power devices are used, like watches, calculator, and such things. So similarly, these are exactly similar thing where CIGS solar cell, where two materials is you have molybdenum here, then you have cadmium sulfide, which is the now principle of all these are exactly same like it was in earlier. So now you have two materials, one is p-type material, one is n-type material, which are actually deposited over each other. So you have copper, indium, gallium selenide here about 2 micron thickness, then above that you deposit cadmium sulfide, then over that you have a front contact of zinc oxide, and then the back contact, and after that there is a glass over glass. So this is the deposition takes place in opposite, say you have a glass, then the back contact, then the front contact, then this way in way, and then you deposit this one, and then the current. Then comes the CDT cadmium telluride solar cells, where also if you see it has two materials, cadmium sulfide and cadmium telluride. One is you use cadmium sulfide, which is n-type material, then cadmium telluride, which is intrinsic, and then for p-type you use a layer of zinc telluride. So you have a zinc telluride layer, you have cadmium telluride layer intrinsic, then you have cadmium sulfide layer, which is n-type. Then you will have on one side you will have glass, another side you have a back contact. So now you have the structure is, which is structure it is? Same structure, P, I, N. So radiation will fall on intrinsic layer. The electron hole pairs will be generated. Those electron hole pair will see a built-in potential due to this N-type and P-type materials, and then these will be the electron hole pairs will be transferred. So to the external electrodes through these materials. So this is efficiency of this are about 20 to 21%, and but the main disadvantage is that cadmium is very toxic. So these are different processes. Then there's another one is the third, fifth semiconductor solar cell. So band gap of gallium arsenide. Third, fifth means one material is having from third group, another material is having from the fifth group. So like gallium arsenide, gallium and arsenide. So gallium arsenide, gallium aluminum arsenide, gallium indium arsenic phosphide materials can be easily varied by composition. So you can deposit one over other, and you can change the composition. You can mix one you can say one element into another element. So the best solar cells are prepared by metal oxide chemical metal organic MOCVD method or by MBE method. Then multiple junction to achieve higher efficiencies for more than 40%. How we achieve this is so in the next slide. You deposit, suppose the band gap of a material is such that radiation will not be absorbed but pass through it. So you let it pass through one material, but then you put another solar cell which is having a lower band gap. So though the radiation will be passed from the top solar cell, but it will be absorbed in the bottom solar in the bottom solar cell in the another layer solar. So multiple junctions are actually junctions are made in order to improve the efficiency. So as I showed earlier, single junctions have efficiency at nearly 27%. But if you have more and more junctions, you can have more efficiency. These cells are highly reliable and radiation resistant. Due to high material and fabrication costs, these cells are mainly used for space or concentrator application. These are not available like for domestic uses because they are very expensive, and they are deposited, they are fabricated by a very you can say involved procedure. So I just want to show one example. Suppose you have a three junction solar cell. Here I am showing one junction is this, another junction is this, another junction is this. So now you see light start from this side, light falls from this side. Now the top cell is having a material indium gallium phosphide, and the band gap is 1.86 electron volt. So what will happen? The 1.86 where it is, it falls suppose here. This is 1.86 corresponding. So this much amount of radiation will be absorbed by this particular solar cell. Now this entire spectrum of the entire solar spectrum will be passed from the top solar cell, but it will reach at the middle cell. Now what is there? It is indium gallium arsenide. The band gap of this material is 1.42 electron volt. So suppose now from 1.8 to 1.4, this 1.4 is there. So this much amount of radiation will be absorbed by the middle junction, and the leftover, whatever is there, the leftover will be passed through this. Suppose the band gap, if the you can say energy is less than 1.4, then it will go to the third layer, which is actually made of the germanium. So germanium, which is having a band gap of nearly 6.65%. So this will absorb up to somewhere here, up to where it falls six up to this somewhere. And then anyway some part will be left. So this way what you have achieved by making use of three different junctions, you have enhanced the efficiency. So by doing this kind of multi-junction assemblies, uh, the very high efficiencies of about 43% has been achieved. And this 43% is not actually at normal one sun. When we say one sun means the when irradiation is about 100 milliwatt per centimeter square. But if you concentrate the radiation and you get more concentrated intensity, you get more and more intensity. And if you have like 200 milliwatt per centimeter square, we can say that you have concentrated two sun into that area. So in the same way, if you concentrate the radiation 400 times less in the less area, then it will be intensity will be called as the 400 sun. So this 43% is efficiency for multi-junction solar cell is reported at 400 sun intensity. I think with this we should stop, and we will see the third generation solar cells, that is organic solar cells, DSSCs, quantum dots, maybe in the next class. And in the same class, we will see thermoelectrics also. So if you have any doubts, I'm ready to answer. किधर लिखना है?